Alzheimer's disease begins decades before symptoms appear, yet by the time it's clinically diagnosed, irreversible neural damage has already occurred. The central scientific challenge here is clear. We lack tools sensitive enough to detect the earliest nanoscale amyloid-beta aggregates in the living brain. Traditional modalities like positron emission tomography and MRI are invaluable, but they are fundamentally limited in resolution and sensitivity. This motivated our group to ask, could we leverage quantum sensing technologies, which is an emerging field, specifically nitrogen vacancy centered in diamond, to detect Alzheimer's pathology at its very onset? Our purpose was to rigorously test the feasibility of this idea. To do so, we built a multi-scale computational framework that spans three levels. First, biophysical modeling of amyloid mimetic magnetic classes in brain-like mediums. Then, noise-aware quantum simulations of optically detected magnetic resonance. And lastly, inverse optimization function to identify sensitive configurations that maximize detection probability. To our knowledge, this is the first pipeline ever that goes from depot level physics all the way to the actionable engineering design route for nitrogen vacancy diamond biosensing of Alzheimer's pathology. We began our methodology by modeling amyloid-beta clusters labeled with magnetic nanoparticles. Each cluster consisted of 10 to the power 5 to 6 dipoles, randomly packed in 3D dimensions and distributed at densities ranging from 50 to 250 clusters per cubic millimeter. These parameters were chosen to match biologically plausible distributions observed in early Alzheimer's reported in the literature. Then we calculated special magnetic field distributions using discretized Biot-Savart integrals within a brain-like dielectric medium that incorporated Gaussian heterogeneity. Gaussian heterogeneity allowed us to capture realistic variability in local tissue environments in human brain. Next, we constructed a Monte Carlo simulation of optically detected magnetic resonance, or ODMR. Importantly, we did not assume ideal detection. Instead, we incorporated the three dominant noise resources: potential noise, line width broadening, and microwave jitter. We identified these noise sources as the real values in our laboratory ODMR setup. Running 10,000 stochastic trials in our Monte Carlo simulation, we generated contrast distribution and estimated the probability of detection under realistic experimental conditions. Lastly, we performed inverse optimization. By systematically varying nitrogen vacancy depth and mean layer thickness and integration time, we identified parameter regimes that robustly maximize detection probability across biologically relevant cluster density. Our result contains three key points. Our simulations show that amyloid-beta mimetic clusters generate detectable magnetic fields with peak amplitudes up to 13.8 nanotesla at 250 amyloid-beta clusters in 1 cubic millimeter, and median values of 4.4 nanotesla at biologically relevant densities, which is 100 amyloid-beta clusters per cubic millimeter in early Alzheimer's disease. Second, detection was robust even under noise. Remarkably, 100 distorted clusters in 1 cubic millimeter, the probability of detection exceeds 95% across 10,000 Monte Carlo trials. These results demonstrate that NV diamond sensors are not only theoretically sensitive, but practically feasible under noisy conditions. Third, optimization analysis revealed clear design rules. Shallow NV depths and thinner layers consistently improved sensitivity, while integration time exhibited diminishing returns beyond the millisecond scale. These quantitative trade-offs define the engineering space for building real biosensors. Our results collectively established the biophysical plausibility and engineering feasibility of quantum magnetic biosensing for Alzheimer's disease. Our contribution is not just a simulation study. It's an end-to-end framework that connected biophysics of dipole classes, the stochastic realities of ODMR detection, and the optimization of sensor design. In doing so, we provided first computational roadmap for translating NV diamond quantum sensing into a diagnostic tool capable of detecting Alzheimer's pathology at the clinical stage. This has the potential to fundamentally shift the diagnostic timeline of the disease and impact the lives of millions of Alzheimer's disease patients. Of course, our work has many limitations. Our models assume simplified cluster geometries and do not yet incorporate in vivo background magnetic noise. This is because our study is a computational framework for an NV diamond quantum sensing for Alzheimer's disease. We believe that future work should focus on coupling this framework to NV fabrication constraints, refining biological realism, and ultimately validating predictions in ex vivo and in vivo systems. Overall, we believe that future work should experimentally validate our computational results. In summary, our study transforms NV diamond biosensing from a theoretical concept into a quantitative engineering roadmap. By defining the detection threshold, noise limits, and optimal sensor parameters, we bring quantum sensing one step closer to enabling pre-symptomatic Alzheimer's disease. Thank you.